কত ইউনিয়ন কত এটা
AI
হ্যাঁ
AI
AI how AI is the union what is the set A1 here A1 টা কত A1 is the set of first one natural number so A1 is singleton one what is A2 A2 is the set 1 2 okay A3 is the set 1 2 3 okay and similarly A4 A5 like that what is A100 is the set A1 2 3 4 up to 100 okay so if you take the union of all this এতটুকু যদি ইউনিয়ন নাও তাহলে কত হলো union I goes from 1 to 100 of AI what is that huh it will be A100 okay because all these are actually subsets of this okay. This will be A100 okay here this process continues here I belongs to natural number this process is continuing okay so A1 is a subset of A2 subset of A3 subset of blah, 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 this way okay so every time I take the intersection of union of these two I get this union of these two I get this okay so that way the process continues ultimately what I will get as the union
AI
you can exactly show this union is AND okay. Right this union is actually AND take any natural number so how to show that these two are equal take an element from this set show that it is in this set so that is obvious because each AI is a subset of natural number so their union is a subset of natural number take an element from this set okay then you can show that this element also belongs to one of these sets or the union here okay take any element n here n belongs to natural number be any element then n belongs to which set is it 1 2 3 up to so it's obvious n belongs to this set okay so n belongs to an always n always belongs to an so if n is there in one of the members n will be there in the union okay union contains all the elements which are there in each of these sets okay all elements right so we already know n belongs to an and so n also belongs to this union so any natural number belongs to this okay so this is a subset of this is also a subset of this okay so this union is actually n what is the intersection so intersection will contain elements which are common to all of this all the sets so which is the only element which is common to all the sets is 1 okay. Because every other set also contains 1 okay but 2 is not there in this set it doesn't 3 is not there in this set also this set also okay so this intersection is actually singleton 1 that is how it is this is the notation okay. So using these notations we can proceed for this partition okay we will define the partition again partition of a set partition of the set okay let capital S be a non-empty set non-empty set then a partition of S partition of capital S is a collection so let us write it as this AI such that I belongs to capital I is a collection of non-empty subsets of S satisfying the following then a partition then okay let S be a non-empty set then a partition of S is a collection AI such that I belongs to capital I okay where I is an index set okay so I is an index set is a non-empty index set non-empty index index. It means there are some members in this. Partition cannot be empty. Okay. So this I has to be a non-empty index set. Okay. Of non-empty subsets of S satisfying the following. So number one condition was they are mutually disjoint. Okay. Pairwise disjoint. So if we take any two members from this collection, they should be either equal or they should be disjoint. Okay. That is what we will write. Suppose I take the member A1, you also may select the member A1. Okay. In that case, intersection is not empty. Intersection is A1 itself. Okay. So that is what we will do. Satisfying the following: AI intersection AJ is equal to phi for all I j inside capital I with I not equal to j. So if you take two sets having different index, okay, then they have to be disjoint. Okay. If I and j are equal, then AI and j are also equal. No, there you have picked up the same set. Sure. If suppose I select A100, you come from somewhere and select another element, that also comes out to be A100. In that case, their intersection is same, no? A100. So whenever I and j are not equal, AI and aj have to be disjoint. Okay. So AI intersection aj is empty for all ij in I with I not equal to j. Okay. Number two is their union is the whole set. Okay. So union of I belongs to capital I of AI. This is equal to the whole set. Okay. Right. The union of all these sets is the whole set. So what can you say here? Thus, a partition. So in language, how we can say partition of S is a collection of subsets, non-empty subsets, non-empty pairwise disjoint. Okay. Pairwise disjoint subsets of S whose union is so in language we can say this way. So a partition of S is a collection of non-empty pairwise disjoint. Pairwise disjoint meaning you take any two, if they are not equal, they will be disjoint. Okay, that is the. So pairwise disjoint subsets of S whose union is S. Okay, in the second condition. So for example, we have seen earlier day also. Suppose S is the set 1, 2, 3, and you take P equal to say singleton 1 and singleton 2, 3. Okay, this is a partition. This is a partition. Partition of S. So this one non-empty, right? And their intersection is empty, and their union is the whole set. So this is a partition. Okay. Another example, last day we had done. Suppose S is equal to the set of natural numbers. Then we had taken say singleton 1, singleton 2, singleton 3. Okay. So how do you write? I write this one as singleton n such that n belongs to natural number. Okay. This is a partition of n. Okay. Is a partition of the set of natural numbers. Okay. They are mutually disjoint and their union is the set of natural numbers. Okay. This is a partition of n. Okay. Another example, given any set capital S and phi not equal to A is a subset of S. Okay. So A is a non-empty subset. Phi not equal to A is a subset of S. Okay. That means whenever I write this, it means that A is a non-empty subset of S. Okay. That is the phi not equal to A subset of S. A is a non-empty subset of S. Given any set S and phi a non-empty subset of S, the set A together with that, which set should I take so that it becomes a partition? Is a partition of S. Subset, proper subset. Okay. Subset not equal. Okay. So this is the symbol for proper subset. A is a proper subset. A is a non-empty. A is a non-empty proper subset of S. Non-empty proper subset. So the subset is not equal to the whole set. Okay. So non-empty proper subset. Right. So is a partition of S. So which set should I take? Because S minus A. This is the complement. Okay. A complement. You take A, then you take the complement of it. Okay. So why do I require it to be a proper subset? What happens if I take S here? S is also a subset of S. In that case, what will happen? Why it is not a partition? S, comma S complement. Why it is not a partition? Complement of one? Complement phi. Okay. The complement of the universal set is phi. Okay. That is why I need a proper subset. Okay. So I need both of them to be non-empty. Okay. So given any set, you take a proper subset, take its complement, then you get a partition. So many partitions are there. Okay. So now you see recall the equivalence class. Okay. I had given one example, something like this. S is the set 1, 2, 3, and R is the relation. R is the relation, say 1, 1. 2, 2, 3, 3, and this is the relation, and 1, 3, 3, 1. So here, what is the equivalence class? This is the equivalence relation. What is the equivalence class of 1? 1 and 3. Okay. Equivalence class of 3. That is also 1 and 3. And equivalence class of 2 is only singleton. Right. So 1 and 3, they belong to the same equivalence class. Sure. So they are related. Okay. Right. So whenever so that means what? This equivalence class 1, 3, it can be represented as this equivalence class of 1, or it can be represented as equivalence class of 3. Okay. So the same equivalence class can be represented in two different ways. So this ekhane bracketed bhitre jeta lekha hoyche, the number that I write here in the bracket is called a representative of this class. Okay, we class is representative. Okay, something like class monitor. Suppose you have a class school and we select some representative which represents this class. Okay. So it may happen that in the next month we select some other member from that class. Okay. So something like that. So the same equivalence class can be represented by different elements of the same set. Okay. Right. So whenever we write this symbol, the number that we write here is called the representative of this class. Is called a representative. So an equivalence class may have many representatives. Unequal representative thakte pare. Okay. For example, this modulo a congruent to 5 divides a minus b, this type of relation that I had done. So there you had seen the equivalence class of, if you take the set as Z and R is the relation, A comma B belongs to the relation if and only if 5 divides a minus b. Okay, in that case you had seen what is the equivalence class of 0? It was the set of 5n such that n belongs to Z. We have already shown this. What is equivalence class of 5? This is also same. Okay. 5n such that n belongs to Z. Okay. Similarly, equivalence class of this 10 was also this, no? Equivalence class of 10. This was also 5n such that n belongs to n z. Okay. So 0 is also a representative of this class. 5 is also a representative. Okay. 10 is also a representative of the same class. Okay. So the same class can be represented by infinitely many elements. Okay. So all multiples of 5 will represent this class. Okay. Clear? Similarly, the class 1 is the set of 5n plus 1 such that n belongs to z. No? So 1 is a representative of this class. Okay. Another representative is 6. Okay, class 6. This is also the same class. 6 also represents the same class. Similarly, minus 4. Minus 4 also represents the same class. Minus 4 minus 1 is minus 5, which is divisible by 5. So minus 4 also represents this class. Okay. So any number which, when divided by 5, leaves the remainder 1. Okay, is a representative of this class. Here, any multiple of 5 is a representative. Here, any number which, when divided by 5, gives the remainder 1 is a representative. Okay. Right. So, when I want to represent the partition of z, okay, the partition of z will be means z can be written as union of this all this, no? Union of all these equivalence classes. Okay. 0, 1, okay, 2, like that. You can continue. Union with 100, okay, like that. So we can take all members, even the negative ones also. Okay. So it is not necessary to take all the members. Okay. It is sufficient to take only the representatives. 0, 1, 2, 3, and 4. Okay. Right. This 0 represents all the numbers which are multiples of 5. 1 represents all the numbers which leave remainder 1 divided by 5. Okay. So z can be written as union of only these 5 classes. Okay. So we select the representatives so that each class is represented only once in the union. Okay. In that case, we can identify a partition. Okay. Right. So it is important for us to select the representative. Okay. This is what we do. So let us write something about this. Note that if R is an equivalence relation, on a non-empty set S, set S, and equivalence class of A. If X belongs to equivalence class of A, then X is called a representative of the class A. Okay, equivalence class of A. X is called a representative of the equivalence class of A. Class of A. Right. Similarly, if A belongs to equivalence class of X, then A is called a representative of the equivalence class of X. Okay. Right. So in an equivalence, under equivalence relation, so the same equivalence class can be represented by various representatives. Okay, representatives. So now let us define something called this. So suppose you consider equivalence classes as being something like this. These are the lines, parallel lines. Okay, suppose this is one equivalence class. So this is the class A, this is class B. Okay, they are different. They are disjoint equivalence classes. Okay, like that. So I can select one representative from each class. Okay, I select one representative from each class. Okay, so maybe I draw something like this. Okay, so if two parallel lines are intersected by this type of line, what is this line called? Known as geometry. If two parallel lines are intersected by another line, what is this line called? Transversal. Yeah. So this line is called transversal. So using that concept, using this concept in mind, okay, we can define transversal of an equivalence relation also. Okay. So what we are doing for this equivalence class, we are selecting one representative. Okay. For the other equivalence class, we select exactly one representative. Okay. For each equivalence class, we are selecting exactly one representative. Okay. So that there is no confusion which member represents the class. Okay. So this is what we will write now. Then a set T, which is a subset of the whole set. A subset or T subset of S is said to be a transversal for the equivalence relation R. Equivalence relation R if T contains exactly one member or exactly one representative. If T contains exactly one representative from each equivalence class. Each equivalence class. So we select a subset of S. Okay. আমি একটা representative নিলাম. There are so many equivalence classes when you consider an equivalence relation. Okay. They are maybe finite, maybe infinite. Okay. But what I do for each equivalence class, I take only one representative. Okay. Say for the class 0 with respect to modulo 5, I take the representative as 0. Okay. So if I encounter class 5, I will not take 5 from there. I will take only 0. Okay. So for each equivalence class, suppose this is the equivalence class of 0 with respect to that modulo relation, modulo 5 relation. Okay. This is all these are distinct. Okay. So when I encounter equivalence class of 5, I will stop. Okay. I will not take anything from here. Okay. So only these are the representatives. Okay. So from here I have taken 0 as the representative. From here I have taken 1 as the representative. Okay. From here 2, 3, 4. Okay. So what is the transversal for this equivalence relation? It is 0, 1, 2, 3 and 4. Okay. This is the transversal of this equivalence relation. Okay. Okay. Congruence modulo 5. Okay. Under that relation, this set is the transversal. Okay. So it is the set which contains exactly one representative from each equivalence class. Okay. Okay. From each equivalence class of R. Okay, so we will need this concept, then we can solve that problem in a better way. Okay, systematic way lecture. So now let us go to this fundamental theorem of equivalence relation. Theorem of equivalence relation. Equivalence relation. Okay, so an equivalence or the equivalence classes of an equivalence relation. Equivalence relation on a non-empty set. On a non-empty set. Non-empty set say as constitutes a partition of S. A partition. And conversely, given a partition P of S, there exists an equivalence relation on S such that its equivalence classes are precisely the members of P. Such that its equivalence classes are precisely the members of P. Okay, the members one is the sets in. So this was the fundamental theorem. Given an equivalence relation, the equivalence classes will form a partition. And given a partition, there is an equivalence relation such that its equivalence classes are precisely the members of P. Okay. So the proof. The first part was almost okay, but we have to include that transversal. So okay. So let E is a set of all equivalence classes. Equivalence classes of all equivalence classes in S with respect to the relation P. Right. So we know our so each equivalence class is non-empty. Okay, so we know class A is not equal to pi for all A inside. Okay. Right, each equivalence classes are non-empty. Okay. Since A belongs to equivalence class of A, okay, for all A. Okay. So this already we will see because A comma A belongs to R. So we know class A is not equal to pi. So this I E is a collection of non-empty sets, non-empty subsets of this. Right. Next, I have to show any two members here are either disjoint or identical. So let class A, class B belongs to E. Be any members. So if class A not equal to class B, then what I have to show? Then I have to show that their intersection is class A not equal to class B. Then their intersection has to be empty. Okay. Or so it's something like this. If class A is not equal to class B, then I have to show class A intersection class B is empty. Okay. Again, so I have to show that if class A is not equal to class B, then their intersection has to be phi. Okay. Equivalently, if their intersection is not phi, then they have to be equal. Okay. So that's equivalent. So that's what I have to show equivalently. Okay. So let me write it the other way, the contrapositive way. This be any members. So if class A intersection class B is equal to phi, okay, then they are disjoint. Okay, then we have nothing to do. We have nothing. That class A intersection class B not equal to phi. Okay, not equal to phi. Then this part you can show. I have already shown. Then show that class A is equal to class B. Okay. So what you have to do, you have to take an element from A, class A, and you have to show that it belongs to class B. Take an element from class B, you have to show that it belongs to class A. Okay. So this part you have completed. I have already shown this. Okay. So I can write after you do this. After that you can write. So the sets in S in E are either disjoint or identical. Either disjoint or identical. Okay. Also, given any A inside S, we have. So now I have to show that their union is equal to S. Okay. So we have A belongs to equivalence class of A. Given any A in S, we have A belongs to equivalence class of A. Okay. So therefore, singleton A, this is a subset of equivalence class of A, which is again a subset of S for every A inside S. Okay, so this part lastly also we have done. So A is an element of equivalence class of A, so singleton A will be a subset. Okay. Next you can take the union. Union of A belongs to S of singleton A. This will be a subset of union of A belongs to S of equivalence class of A, and this is a subset of S. This is a universal set. So S union like that. It is S only. Okay. Union of S with itself. So ultimately, what I have got, this side is actually S. S is a subset of this. Okay, and this is the subset of S. Now union of all singleton subsets of S is the set S is. Okay, so from here I have got S is the union of A belongs to S of singleton. So the union of members in E is equal to S. Okay. So everything is satisfied. E satisfies all conditions of partitions. Just what is left? There are some repetitions here. Okay. The same equivalence class may occur many times in this if we write it this way. Okay. So we have to avoid partition. Okay. So this is where we will just choose representative from each class. Okay. Extract a representative instead of putting repetitions here. Okay. So I don't want something like it's not required. Something like this is not required. A belongs to S. This is not required. We will just take representatives. Okay, for each equivalence class. Okay. So up to this, is it okay or not? First, I have shown that each equivalence class is non-empty. Okay, this is a property. Then I have shown that if their intersection is non-empty, then they have to be equal. So the equivalence classes are either disjoint or they are identical. Okay, this is what we have shown. So they are pairwise disjoint. So this is the second condition for the condition for partition. And the last one I have shown that their union is the whole set S. Clear? Next we have to conclude that means from here I will not write E is a partition, because in E I have taken all equivalence classes. In this union I have taken all equivalence classes. So many repetitions are there. Okay, so just one line I have to add that we will not consider repetitions here. Okay, we will take only distinct equivalence classes here. So let T be the transversal. Be a transversal of R. Be of the equivalence relation R. Let T be a transversal of the equivalence relation R. That is, T contains, what is a transversal? T contains, or that is T subset of S contains just write it this way. Let T subset of S be a transversal of the equivalence relation R. That is, T contains exactly one representative from each equivalence class. Okay. One representative from each equivalence class. Each equivalence class. Then one can be written as one can be written as equal to union of A belongs to T, of singleton, equivalence class. So here I have avoided the repetitions. Okay. So this union contains all distinct equivalence classes. Okay. So instead of taking A from the whole set, we are taking A from one of the transversals. Okay. So there may be many transversals. So that is why I have written let T subset of S be a transversal of the equivalence relation R. Okay. So T contains only one representative from each equivalence class. So therefore one can be written as this. Okay. Hence the collection of distinct equivalence classes. Okay, so we have collected only distinct equivalence classes. We have avoided the repetitions. Okay. Hence, the collection of distinct equivalence classes, let us write it as say E. Okay, or yeah. So the collection of distinct equivalence classes C equal to class A such that A belongs to T. Is a or forms a partition so the equivalence classes, they form a partition of this. Okay. So we will take only distinct equivalence classes. Okay. This is what we will do. Collection of distinct equivalence classes C equal to class A such that A belongs to T. Okay, that means we are taking only the representative, okay, not other elements. For each class, we are taking only the representative. Okay. So A belongs to. So this forms a partition of this. Okay. So one part is done. The other part is this. Conversely, let P equal to the set of AI such that I belongs to capital I. Okay. This be a partition of S. Okay. where this I is a, what is I? I is a non-empty index set. Non-empty index set. So we have considered a collection of a partition of the set S. Right. This is a partition. Okay. So now we will define an equivalence relation on S. Okay. We define the relation R on S as A comma B belongs to R if and only if. Okay. So last day what I had written, if and only if they belong to the same subset in this partition. Okay. This is what we have written. So last day I had written it in language. Today I will write it with symbols. Okay, it will be easier. So last day I had written if and only if A and B belong to the same subset here, the same member of P. Okay, so that I can write it this way. If and only if there exists an I inside capital I such that A comma B belongs to AI. Okay, that means A and B belong to the same member of the partition. Okay. So this is the same way of writing, that is A and B belong to the same member of P. Belong to the same member of P. Okay. So last day I had written it in language, so that was becoming lengthy. Okay. So it's better to write it this way. A and B are related if we can find an I such that A and B belongs to that AI. Okay. So A and B belong to the same member of P. So R is an equivalence relation. So how will I show? I will show that it's reflexive. Okay. So R is reflexive. Why? R is reflexive. Since P is a partition, partition of S. Okay. So since it is a partition, so what is S? S will be the union of all this. Na? Union of I belongs to capital I of AI. Okay. Since P is a partition, so S is the union of all these sets. So if I take an arbitrary element of S, so let A belongs to S be any element. Then A belongs to union of I belongs to capital I of AI. Okay. So this means that A belongs to AI for some I. For some I. A is an element of the union. That means it is there in one of the sets. Okay. So from here I can write A belongs to AI for some I. Okay. So that is A and A comma A belongs to AI for some I inside. And this means that A comma A belongs to R. A and A, they belong to the same set. So it's just like saying same thing twice. Okay. We are saying the same thing twice. Okay. So it's obviously reflexive. Okay. A comma A belongs to R. So therefore R is reflexive. Okay. Next, you try to show that R is symmetric. So symmetric is also simple. You take A comma B belongs to R, so that BA also belongs to R. So how will you show that R is symmetric? R is symmetric. So for that, I have to take two elements which are related. Okay, let A comma B belongs to R. Okay. Then, so what is the meaning? The meaning is that A comma B belongs to AI for some I. For some I inside. Okay. A A and B belong to the same AI. So from here, what can you say? I want something like BA. A and B belong to AI. Is it same as saying B and A belong to AI? The same thing. A and B belong to AI. Suppose I say something like, suppose A and B belong to the say maths honors first year. It is same as saying B and A belong to the maths honors first year. Okay, the order is not important. Right? So B comma A belongs to AI for some I inside. Okay. So this means that B comma A are related. So R is symmetric. If AB is related, then BA is symmetric. R is symmetric. Okay. Next, I have to show that R is transitive. Okay. So R is transitive. So R is transitive. How will I show that AB BC belongs to R. Okay. Suppose AB and BC belong to R.